Hello everyone, welcome to my video. In this video, we will explore the concept of linear impulse and linear momentum, which could be new concept to many of you. We looked at work can be calculated by U equals to force times distance. This is essentially integrating F with respect to displacement. At that time, 2 videos ago, I also briefly mentioned that the other type of integration with F can be done is integrated with time. So here we are. We have G equals to F times T, where we call the Ft term is the linear impulse and G is a linear momentum. We're going to spend this time in this video to explore both terms. We will start with F equals to ma. The acceleration can be replaced by dv over dt. We know that. That's nothing new. So we can sub in to rearrange a little bit. We now have the sum of F, sum of force, equals to d dt, d over dt, mv. Then we can define the mv term, give it a new name, called G, the linear momentum. Then we can tidy up the equation to become sum of F equals to G dot, or d over dt, G, or G, the derivative of G over time. The meaning of the equation is the resultant force acting on the particle equals to the time rate change of linear momentum. A reminder here, if you have been paying attention to those bolded fonts, thank you. You should notice linear momentum G is a vector. Let's take a quick look at one example here. Using G equals to mv, we can calculate the linear momentum of this baseball at this instant is 5.8 kilogram meter per second. Of course, we are ignoring the gravity here, and the ball is flying horizontally. On the other hand, we also have sum of F equals to G dot, or equals to mv dot. This tells us the G linear momentum will change only because the resultant force, either direction or magnitude. This is similar to F equals to ma, Newton's second law. The resultant force is the reason for changing acceleration because the linear momentum was derived from Newton's second law. They are closely related. Here are 3 directions I want you to pay attention to. The direction of resultant force, the direction of linear momentum rate of change, and the direction of velocity rate of change. But you can see probably already, they are the same thing as expressed in this equation here. Think about using a bat to hit a ball. Intuitively, you know the ball will change trajectory and velocity. In dynamics, we see that because the force imposed on the ball by the bat, the ball's linear momentum G changed, and the ball's acceleration, the rate of change of velocity, changed. Okay, so it's kind of hard to wrap your head around with it, especially if you are the first time seeing concept like this. So take your time, pause the video, read those sentences over and over again. Since I mentioned the similarity between F equals to ma and G equals to mv, same as what we did before, we can break forces into different components. We can do the same for linear impulse. We can break it into different directions, gx, gy, and gz. Let me provide a simple example here. The baseball bat hit the ball with a 3,000 Newton at an angle of 30 degrees below x-axis positive direction within 0.02 seconds, a very short period. So we can calculate gx and gy using sum of F equals to g dot. We can calculate it, gx dot and gy dot. However, in order to solve further, knowing more information, we need to prepare one more thing. Going back to the equation we have obtained, we can integrate this equation from time t1 to t2 to reveal the change in linear momentum during that time. As a result, we are ending up with this new equation we can use to calculate change in linear momentum. And this equation tells us that change in linear impulse equals to the change in linear momentum. Okay, or rearrange it, we can say that linear momentum plus change in linear impulse gives us the final linear momentum. Same thing as before. We can break linear momentum into different axes for easier calculation. Sometimes you will see forces that can be treated as constant force during an extremely short time period, right, such as the 0.02 second. Like within that short period of time, we can call them the impulsive force, and they are constant, or they can be treated as a constant within that short period of time. Sometimes forces can change over time if we are considering a longer period of time. Then we need to properly to do the sum of f dt part with integration, or you can use graphs if graph is provided to calculate the area under the curve, which is the same as doing numerical integration. Now we are ready to do this again. We can use the equation we just developed to find out the velocity after the baseball was hit. Subbing the number proper values into each variable, we can get the velocity after hitting the bat. Clearly, you can see the velocity almost 400 meters per second on the x direction and 200 meters per second on the y direction. Altogether will probably over 400 meters per second. Overall, this number clearly does not physically make sense, because I just made them up and to demonstrate how this equation can be used. So you can get the idea. But as a practice, you can think about why this number that I made up does not make sense. Okay, as a practice for you. Similar to free body diagram, the linear momentum equation can be demonstrated using vector graphs. Why is it similar? Because remember, linear momentum is derived from F equals to ma. So linear momentum and force, they are closely related. They are both vectors. From the graph perspective, we are essentially adding the initial momentum vector with the resultant linear impulse vector created by the external force to get the final momentum vector. Okay, you can draw them out same as you draw the free body diagram. Sometimes, if there's no resultant force or no external force, or resultant force is 0, then we'll end up with G1 equals to G2. There is no change in linear momentum. This can happen. In this case, we say the linear momentum of particle is conserved, and this conservation of linear momentum can be true for the entire system, or sometimes just for certain direction. So it is possible that, for example, linear momentum is conserved in the x direction while lost in the y direction. And this is called the principle of conservation of linear momentum. Conservation of linear momentum is especially useful when considering collisions. Right? Looking at these two objects that they collide each other, based on Newton's third law, the force acting on them are equal in magnitude and opposite in direction. Therefore, we can look at these two bars as a whole system, and then within this whole system, the total linear momentum is conserved. So we can use G1 equals to G2 to do the calculation. Here's a list of recommended readings. Please take a look. Thanks for watching. I'll see you next time.